The question says that give the magnitude and direction of the net force acting on a drop of rain falling down with a constant speed. So here a drop of rain is falling under constant speed. We all know from Newton's first law that a body is at rest, continues to be at rest until or unless there is an unbalanced force acting on it, or a body when it is in motion, then it will remain in motion with constant velocity until or unless there is some unbalanced force acting on it. So in case it is falling down with a constant speed. The speed is not changing when it is falling down. We all know that it is under influence of force of gravity that is pulling the raindrop towards the ground, and also it is acted upon by frictional force of air. That's why these two forces are getting balanced. Hence, the raindrop is falling with constant speed, keeping its net force equal to zero. So its magnitude and direction. Magnitude is going to be zero. Since it is zero, it is having no direction. Now, in second case, we have a cork of mass 10 gram floating on water. Again, cork is floating like this on water. It is having some mass, so it should have gravitational pull towards downwards. Also, it is acted upon by buoyancy force, which is pushing it outwards, and these two forces are balancing each other, so making the net force zero. Now, in third case, we have a kite skillfully held stationary in the sky. So we see from the Newton's first law that a body continues to be in the rest if it is at rest initially until or unless some unbalanced force is acting on it. So here the body is stationary in the sky. So until or unless there is some unbalanced force, it is not going to move, and hence it is stationary. So we can say that the net force acting on it is zero. Now, in fourth option, we have a car moving with constant velocity of 30 km per hour on rough road. Here we see again that the velocity is constant, though engine is pushing it forward. Also, due to rough road, there would be certain amount of frictional force acting in various dimensions from various direction. So in order to keep that motion constant, the forces acting on it is balanced by the motor. That's why the velocity is constant, or we can say that the car is moving with constant velocity and its net force is zero. Now in fifth option, we have high speed electron in space, far from all materials, object, and free of electric and magnetic field. So here the particle is assumed to be in outer space, free from all the materials and any other interaction that it can have. So it automatically says that the force is going to be zero because it is not interacting with any kind of material or any kind of magnetic or electric field which would have generated force. So its net force is going to be zero. So in every case, the net force is zero in this question. Thank you. The question says that a pebble of mass 0.05 kg is thrown vertically upwards. Give the direction and magnitude of the net force on the pebble during its upward motion, downward motion, and the highest point where the body is at momentarily rest. And do your answers change if the pebble was thrown at an angle of 45 degree with the horizontal direction? Ignore air resistance. So here two cases are to be discussed. At first, when the pebble is thrown vertically upwards, and second, when the pebble is thrown at an angle of 45 degree with the horizontal. So let us discuss the first case. So let us first discuss. Yeah. So this is the coordinate axis x and y. We are assuming that the gravitational force is acting downwards and pebble is thrown upwards against gravity. Now there are three cases over which we have to discuss: the upward motion, the downward motion, and the highest point. So we know that when pebble will be thrown upward, its velocity will diminish with time, and there will be a point when it will become zero, and that point is called as the point of highest reach, and then it will go down to the ground. So while moving upwards, its velocity is decreasing, or we can say that it is having negative acceleration. It also means that the acceleration is acting in the opposite direction of the velocity. So velocity was in this direction, so acceleration is downward direction, and acceleration is due to the force of gravity that is always present, and that force of gravity is due to the mass. The expression for force of gravity would be mass times acceleration. This is g. So mass is 0.05 kg, and let us assume the acceleration of gravity to be 10 meter per second square. So its force would be 0.5 Newton. So this force is always acting in the downward direction irrespective of the position of the body. So when it is moving upward, then also this force is acting, which is leading to the deacceleration of the body. And when it is at the topmost position, momentarily at rest, then also this force is acting. And when it is moving downward, then also this force is acting, and this force now results in the increase in velocity with time, because the velocity is in same direction as that of the acceleration. So in all the cases, in first case there is a force of 0.5 Newton acting on the pebble. Now in second case, when it is thrown at 45-degree angle, so let us assume that the ball is thrown like this. It will have a trajectory like this. This is 45-degree angle. This is the upward motion. This is the point of highest reach, and this is the downward motion. Now here again we see that the force would be acting downward because it is a gravitational force and it has mass. The pebble has mass, so it is always going to be acting in the downward direction. Now what would change here is at the point of highest distance away from the ground, it is not going to be at rest because it has some x direction component of velocity, which is not being affected by the force, because force is not acting in the x direction, it is acting in the y direction. So this component of velocity would make the pebble move in x direction irrespective of the height. Since we have to ignore the air resistance, so there is no any other force acting on the body, so it will have a motion in the x direction, which results due to the x component of the velocity, since it is at an angle of 45-degree. Now rest, the force is acting in the same downward y direction of 0.5 Newton in this case also. Thank you. The question says that give the magnitude, direction and net force acting on a stone of mass 0.1 kilogram just after it is dropped from window of a stationary train. And the second question is just after it is dropped from a window of a running train at a constant velocity. And the third is just after it is dropped from window of a train accelerating with 1 meter per second square. And the fourth is lying on the floor of a train which is accelerating with 1 meter per second square, the stone being at rest relative to the train. We have to neglect air resistance throughout. So let us draw some diagrams that will explain the question a bit. So in case A, let us assume that this is the train and this is the reference of ground. So the train is stationary, that is v equals to 0, and the stone is dropped. So we have to find out magnitude and direction of the net force acting on the stone. So this stone was stationary and we all know that gravitational force is acting whichever body has mass. So the only force present here is the acceleration due to gravity or the gravitational force. So force would be equal to mass times acceleration, and that would be 0.1 kg multiplied by 10 meter per second square, that is 1 Newton, downward direction. Now in case B, we have just after it is dropped from the window of a train running at constant velocity of 36 km per hour. So in this case we have this train, it has a velocity of 36 km per hour. Let us assume that the velocity is in this direction. Now we see that the velocity is constant. Also, when the stone gets detached from the moving object, that is a train, then it has got nothing to push. So the constant velocity represents no acceleration in this direction, and the only acceleration that is being acted upon is the force of gravity, because it is under free fall. So just like before, its force would be force equals to mass times acceleration, which is in downward direction, that is acceleration due to gravity, and that would be equal to 1 Newton. Now in third case we have just after it is dropped from a window of a train accelerating with 1 meter per second square. Now this time we have got acceleration of the train, and the stone is thrown. So as soon as the body gets detached from the train, its acceleration is gone. So the case when the stone is thrown out of the window, then again only one force is acting on the stone, that is the force of gravity, and again the magnitude is equals to force equals to mass into acceleration. That would give us 1 Newton, because as soon as it gets detached from the train, the acceleration is lost, thereby there is no any force because there is no any acceleration. So the only force that is present after it is thrown is due to gravity, and that is 1 Newton. Now in fourth case we have lying on the floor of the train which is accelerating with 1 meter per second square, the stone being at rest related to the train. Now this is a case where stone is here. Let us assume that the stone is here sitting idly, and the train is accelerating with 1 meter per second square acceleration. Now here we see that as the stone is at rest on the floor of the train, so even though the force of gravity is acting in the downward direction, also there is a reaction force that is acting in the upward direction, that is keeping the stone at rest, and that is equal of the magnitude and opposite of the direction of the force of gravity. So these two forces cancel out this time. Since the train has got a net acceleration of 1 meter per second square in the moving direction, so the only force that would be acting is mass times acceleration in the direction of motion, and that would be equal to 0.1 kilogram multiplied by, what is the acceleration? 1 meter per second square. One 0.1 kg multiplied by 1 meter per second square, and that would give us 0.1 Newton. Thank you. The question says that one end of a string of length L is connected to a particle of mass m, and the other to a small peg on the smooth horizontal table. If the particle moves in a circle with speed v, the net force on the particle towards the center is. So we have to assume T here is the tension in the string, and we have to choose the alternative among these. So the question represents, so let us pictorially represent the question here. So this is the overhead view of the table, and in the middle of the table there is a plier. With the plier attached is a particle of mass m, and it is moving in a circular direction with a constant speed, that is v. Now we all know that when a particle moves in a constant speed in a circle, it is known as uniform circular motion, and in this case there is a force acting towards the center of the motion, that is known as the centripetal force, and that is given by mv square divided by r. And there is also a force known as centrifugal force, which is a pseudo force which is acting away from the center, and that is known as centrifugal force. Now these two forces on the particle balances each other so that the particle remains in the circular motion. Now the question is asking that what is the net force of the particle acting towards the center. So towards the center there is this centripetal force that is acting, and the agent that is causing this centripetal force to act is the string, and in the string there is tension which would be away from the, which would be in this direction towards the center, that would be acting on the particle to keep it in circular motion. So the answer would be this T, and the magnitude of tension would be mv squared divided by r. Thank you. The question says that a constant retarding force of 50 Newton is applied to a body of mass 20 kg moving initially with a speed of 15 meter per second. How long does the body take to stop? So the question says that a body, let us assume that body B is moving in direction with a constant velocity, that is 15 meter per second. Now a constant retarding force of 50 Newton is applied on the body. So retarding force is some force which is applied on a body to reduce its speed. So it must be in the opposite direction. So in this direction 50 Newton is applied, and the mass of body is 20 kg. So we have to find out time t that is required to make the body to stop. Time t equals to what at v equals to 0, given that u equals to 15 meter per second. So from the equation of motion we know that v equals u plus at, where v stands for final velocity, u stands for initial velocity, a stands for acceleration, and time t stands for time taken. Now we have to find out acceleration because this is the known value here. So given that a retarding force of 50 Newton is applied, so we know that force has two components, that is mass and acceleration. Mass times acceleration is force. So we have force of 50 Newton, that would be equal to 20 kg multiplied by acceleration. Now acceleration would be 2.5 meter per second square. Now since this acceleration is acting in the opposite direction of velocity, so we can take acceleration as negative in this equation. Now substituting acceleration in this equation, we will have v equals to 15 meter per second minus 2.5 times t equal to 0. Now t would be equal to 15 divided by 2.5 seconds, that would be equal to 6 seconds. So the body will come to rest in 6 seconds. Thank you. The question says that a constant force acting on a body of mass 3 kg changes its speed from 2 meter per second to 3 meter per second in 25 seconds. The direction of the motion of the body remains unchanged. What is the magnitude and direction of the force? So in this question there is a body which is traveling with a speed of 2 meter per second. Now it changes its speed from 2 meter per second to 3.5 meter per second in 25 seconds. Now when the velocity is changing, then there must be some acceleration associated with the body. We have to find out what is the direction of force and magnitude in this case. Now if there is an acceleration, then there must be an agent called force which is causing the acceleration. So from the equation of motion we know that v equals to u plus at, or final velocity equals to initial velocity plus acceleration times time interval. Now here final velocity is 3.5 meter per second, so it would be 3.5, that would be equal to initial speed, it's 2 meter per second, plus a acceleration, we have to find out this, multiplied by time interval, that is 25 seconds. Now acceleration from this equation would be 0.06 meter per second square. So the definition of force says that force equals to mass times acceleration. Here mass of the given body is 3 kg multiplied by acceleration, that is 0.06 meter per second square, would be equal to 0.18 Newton. So 0.18 Newton is necessary for the body with initial velocity of 2 meter per second in 25 seconds to reach its velocity to 3.5 meter per second in 25 seconds. Thank you. The question says that a body of mass 5 kg is acted upon by two perpendicular forces, 8 Newton and 6 Newton. Give the magnitude and direction of the acceleration of the body. Now we know here that forces are vectors and they need to be added by the triangle law, which is for vectors, for finding out the resultant. So let us assume that this is a particle over which 8 Newton is acting horizontally and 6 Newton is acting vertically. We will isolate this particle. Apart from these two forces, there are no other force acting on the body. So now let us add the vectors. So this would be 6 Newton vector and this would be 8 Newton vector. Now the resultant vector would be something like this. Let us represent it by r. So we have been given that these two forces are perpendicular, so the angle between them would be 90 degree. Now in order to find the magnitude of resultant, we will apply the Pythagoras theorem. So the resultant will be of magnitude 8 square plus 6 square under root, and that will be equal to 10. So the resultant would be 10 Newton. Now in order to find out the direction, we will find the tangent of this angle theta. So tan theta would be equal to 6 Newton divided by 8 Newton, and that would be equal to 3 by 4. Now theta would be equal to tan inverse of 3 divided by 4, and that will be equal to 37 degree. Now we can say that the resultant force of 10 Newton would be at an angle of 37 degree clockwise from the 8 Newton force. Also, we have to find out the acceleration of the body. So we have found out the force, magnitude of force, that is 10 Newton. Now force is equals to mass times acceleration. Since mass is 5 kg times acceleration and the magnitude of force is 10 Newton, that will give us acceleration of 2 meter per second square in the direction of resultant force. Thank you. Question says that the driver of three-wheeler moving with a speed of 36 km per hour sees a child standing in the middle of the road and bring his vehicle to rest in 4 seconds, just in time to save the child. Now, what is the average retarding force on the vehicle? The mass of three-wheeler is 400 kilogram and the mass of driver is 65 kilogram. So the situation is like, this is a vehicle. It is speeding at 36 km per hour, sees a child, stops, applies his brake and stops in 4 seconds. Maybe it would be here. 4 seconds is the time interval which it took to come at complete stop. Now we have to find out retarding force. So there must be an edge and there must be a force that would be responsible for reducing the vehicle's speed to 0. So we have to find out the magnitude of that force, and the direction would be simply in the opposite direction of the velocity. So in order to find out the force, we have mass, combined mass of the driver and the vehicle. So it is 465 kg, which constitutes the moving system. Now we just need to know the acceleration, because the force equation would be mass times acceleration. We have mass 465 kilogram and we need to have the acceleration to find out the required retarding force. Now for the convenience, we will convert the units to SI unit. 36 kilometer per hour may be written as 36 times 1000 divided by 3600. That would be equal to 10 meter per second. Now from the equation of motion, we know that v equals to u plus at. Final velocity would be equal to 0. U, that is the initial is 10 meter per second, plus acceleration times time interval, that is 4 seconds. Now acceleration would be equal to minus 2.5 meter per second square. So substituting this acceleration in the equation of force, we will have 465 multiplied by 2.5 meter per second square. That would result in 116.2.5 Newton, or we can say it is 1.2 into 10 raised to the power 3 Newton. So this magnitude of force is required in the opposite direction to bring the vehicle traveling at 36 km per hour to stop in 4 seconds. Thank you. The question says that a rocket with a liftoff mass of 20,000 kg is blasted upwards with an initial acceleration of 5 meter per second square. Calculate the initial thrust force of the blast. So let us proceed with drawing the free body diagram. So let us assume that this is the rocket represented by the dot. In upward direction, in the direction of lift, we can say there is a thrust force, and since it has mass, so weight will act in the downward direction Let us represent it by mg, where m stands for the mass and g stands for acceleration due to gravity. Also, we will be having inertial force which will be acting in the opposing direction of the initial acceleration. So here as the rocket is lifting off, so the rocket would be going up with an acceleration of 5 meter per second square, so force of inertia would be acting in the downward direction. Let us represent it by Fi. We all know that inertia force is equal to the net acceleration times mass of the object. So let us equate both the side of force. So thrust in the upward direction would be equal to mg, that is weight, plus inertia force, that is Fi, and that would be represented as 20,000 kilogram times 10 meter per second square, plus inertia force would be 20,000 kilogram multiplied by 5 meter per second square, and that would be equal to 20,000 multiplied by 15 Newton, that would be equal to 3 multiplied by 10 raised to the power 5 Newton. So thrust should be equal to 3 multiplied by 10 to the power 5 Newton, which will be required to lift the rocket of 20,000 kilogram with an initial acceleration of 5 meter per second square. Thank you. The question says that a body of mass 0.40 kilogram moving initially with constant speed of 10 meter per second to the north is subjected to a constant force of 8 Newton directed towards the south for 30 seconds. Take the instant of force applied to be t equals to 0, the position of body at that time to be x equals to 0, and predict its position at t equals to -5 second, 25 second and 100 second. So this question is about one-dimensional motion. Let us assume that the upward direction is north in this case. Now let us assume that at t equals to 0, the body is here, progressing forward with an initial velocity of 10 meter per constant speed of 10 meter per second. So initially it is traveling at 10 meter per second. Now at this instant t equals to 0, force of magnitude 8 Newton is directed towards south, that is in negative direction, or the direction opposite to that of the motion of the body. So we have to find at first the position at t equals to -5 seconds. -5 here is referred to the 5 seconds before time t equals to 0. So since the force is applied at t equals to 0, so we can assume that time before t equals to 0, the body would be traveling with a constant speed of 10 meter per second. So its position, since it is one-dimensional motion, so its position would be somewhere here, and its position can be found out by displacement equals to velocity multiplied by time interval. Time interval is 5 second multiplied by velocity, that is 10 meter per second. Now it would be 50 meters. So it would be 50 meters behind the initial behind the point at which t equals to 0 it is. Now for t equals to 25 seconds, we know that the force is applied at after t equals to 0, and it is applied till 30 seconds. So at 25 seconds the force would be applied on this body. So let us find out what is the acceleration. Given force equals to mass times acceleration. Now force is 8 Newton and mass is 0.4 kilogram. So acceleration would be equals to 20 meter per second square. And this force is acting southward, so we can take acceleration in the opposite direction of motion. And since it is in one dimension, so we can represent it by sign of negative in this. So acceleration we have calculated. Acceleration is applied with the magnitude of 20 meter per second square from time t equals to 0 to time t equals to 30 second. Now finding the position at t equals to 25 second, we can apply this equation of motion, that is s equals to ut plus half at square. Now we see that u equals to 10 meter per second, which is initial speed, and time interval is 25 seconds. Since the acceleration is constant, so we can apply this equation, half 20 times t square, that is 25 square. Now this would be equal to, so we can do minus here, so this will turn out to be minus. So 250 minus 625 0, or it would be minus 6000 meter. So at time t equals to 25 seconds, the position would be minus 6 kilometer in the backward direction, or minus 6 kilometers. Now let us find out for t equals to 100 second. We have the data here, so we can erase it a little bit. We see that the constant acceleration is applied till 30 seconds only. So let us approach this equation with a graph. Initially, let it be VT graph. So initially the velocity is 10 meter per second, or speed in one direction is 10 meter per second, and deaccelerating force of with an acceleration of minus 20 meter per second is applied till 30 seconds, and we have to calculate the displacement at 100 second. This is 10 meter per second. So we can represent constant deacceleration with negative slope of straight line. Mind it that this graph is not to the scale. And after that, with some constant velocity, after application of the force, since the force is application of force is removed after 30 seconds, so it can go with the constant velocity. Now we can say that the area of VT graph will give the displacement. So the area of this triangle plus this trapezium will give us the displacement in this entire duration. So the area of this triangle would be positive and this would be negative, as this is deaccelerating force, so the body is moving in the negative direction of x-axis. So let us calculate the area of this small triangle first. Let it be represented by O, A, B, this point be C, this point be D, and E, F. So the total displacement would be area of triangle ABC, triangle ABO, plus area of CDFE. So the triangle, so this area would be equal to half times 10 times, we don't know the base or the time at which v comes to 0. So let us calculate this. So v equals to u plus 80, v would be equal to 0 plus initial velocity is 10 plus acceleration is minus of 20 multiplied by time, t equals to 0.5 second. So t would be 0.5 second in meters. So 2.5 meter positive. Now finding the area of this trapezium, we will have half multiplied by summation of these two horizontal lines. So this line would be 100 minus 0.5, so it would be 99.5 plus this line would be CD would be 70 multiplied by this height. Now this height is nothing but the velocity at t equals to 30 seconds. So we can find out with the equation of velocity v equals to u plus 80, u equals to 10 plus minus of 20, that is acceleration times 30 seconds. So this velocity would be equal to minus 590 meter per second. So multiplied by 590, this again would be in meter, and this entire area is in negative side of the axis, so this the area would be negative. Let us calculate this. So it would be 550,000 2.5 meter negative. Now adding these two areas, we will get the position at t equals to 100 seconds. So after summation at t equals to 100, we will get minus 50 kilometers. So the particle is at minus 50 kilometer at t equals to 100 seconds. Thank you. The question says that a truck starts from rest and accelerates uniformly at 2 meter per second square. At time t equals to 10 seconds, a throne is dropped by the person standing on top of the truck, that is 6 meter high from the ground. What is the velocity, acceleration of the stone at t equals to 11 seconds? So here the question is talking about a case where a body detaches from another body that is being accelerated. So let us assume that there are two bodies in contact first, and we are assuming that this body is tight so that no slipping is occurring between these bodies. Now if this body is accelerating with some acceleration, let's say a, the moment body 2 will get detached, it will lose its acceleration. The body 2 will lose its acceleration. Now here the same case is occurring here. Body 1 is the truck and body 2 is the stone. A stone is being thrown by the man. So the moment stone is thrown at 10 seconds, it will lose accelerating and it will go with constant velocity. So we have to find out the velocity at t equals to 11 second and acceleration of the stone at t equals to 11 second. So let us proceed with the solution. So velocity will have two component. One is horizontal component along the direction of moving of truck, and another would be vertical component along the direction of gravity, acceleration due to gravity or towards the ground. So let us represent it by Vx and by Vy. So Vx would be u plus at. Now u would be, since truck starts from rest, it would be 0 plus acceleration is 2. For how much time the acceleration acted? For 10 seconds. So Vx would be 20 meter per second. Similarly Vy, we can calculate u plus at. Now stone is thrown from rest, in this y direction, so it would be 0 plus, so how much time the stone has traveled in air, it would be just 1 second, because at 10 second it was stationary in this y direction. So we can use 10 meter per second square for acceleration due to gravity multiplied by 1 second, so its velocity would be 10 meter per second. Now resultant velocity vector, the magnitude of resultant velocity vector can be given as 20 square plus 10 square under root, and that will come out to be 22.4 meter per second square, meter per second. Now we have to calculate the direction at which the resultant velocity is acting. So the direction of the resultant velocity vector, now we can move this velocity vector here, and this would be the resultant velocity vector. Vr, let us represent it by Vr. So we have this Vx of magnitude of 20 meter per second, and Vy has magnitude of 10 meter per second. Now finding this angle theta would give us tan theta, the trigonometric ratio would give us 10 divided by 20. Now theta would be tan inverse of 1 by 2, that will come out to be 26.6 degrees. And also this theta is equals to this theta, so the resultant velocity vector is acting at 26.6 degrees from the horizontal axis. Now we have found out the velocity vector at time t equals to 11 second. We have to find out the acceleration of the stone at t equals to 11 second. So as we discussed in this picture, that as soon as the body detaches from the accelerating body, the agent that was causing the acceleration with respect to the first body is not acting anymore, so there is no acceleration due to this body. The only acceleration left would be acceleration due to gravity, and it has magnitude of 10 meter per second square in the downward direction. So the net acceleration at t equals to 11 second is 10 meter per second square in the downward direction. Thank you. The question says that a ball of mass 0.1 kilogram hung from the ceiling of room by a string 2 meter long is set into acceleration. The speed of the bob at its mean position is 1 meter per second. What is the trajectory of bob if the string is cut when the bob is at one of its extreme position, and the second is at its mean position? So basically what we have to do here is, this is the ceiling and this is the string which is of 2 meter long, and the speed of bob at its mean position, it's 1 meter per second, and since it has a speed, then it will go to some height at its extreme position. Let us say that the extreme position is represented by m and n, and the mean position be by 0 or by O. Now the first part of question says that what will be the trajectory of the bob if the string is cut when the bob is at one of the extreme positions. So either this position or this position. If the string is cut, then what will happen? What will be the trajectory of the bob? So when the string is cut, at first we should know that when the bob is at extreme position, its speed is going to be 0. So the moment we cut the string, when its speed is 0, then the acceleration due to gravity would be acting anyhow, so it will lead to the free fall of the bob. So in case A, the bob trajectory will be of free fall, because when it is at extreme position, the only force that would be acting on it is mg, the mass and acceleration to gravity, and that will lead to acceleration in the downward direction, and this is the only force that is acting. That is why it is going to be in the free fall. Now when it is at the mean position, then it is having some initial velocity. After the string is cut, the initial velocity is going to be of 1 meter per second. So the warp will be acted upon by gravity, as well as it will move in the parabolic path in this direction, in the moving direction. So in second case, we will have a parabolic trajectory. It will go something like this and fall in the ground. Thank you. The question says that a man of mass 70 kg stands on weighing a scale in a lift which is moving upward with a uniform speed of 10 meter per second, downward with a uniform acceleration of 5 meter per second square, upward with uniform acceleration of 5 meter per second square. We have to find out the reading on the scale in each case, and also what would be the reading if the lift mechanism failed and it hurtled down freely under gravity. So basically the reading on weighing a scale is nothing but the force applied by the man on the ground or on the weighing scale. So let us proceed with the free body diagram in all the cases. So in first case, since the body is traveling with uniform speed, so the net force on the body must be 0. Now the forces that is acting on the body are, first is acceleration due to gravity, the force due to gravity, that is mg, and the counter force or the reaction force is equivalent to mg, that is applied by the weighing scale. So the force that is acting downward is mg, or that is equal to the weight or mass times gravity, 70 kg multiplied by 10 meter per second square, or 700 Newton. In the second case, we have the lift is moving downward with a uniform acceleration of 5 meter per second square. So the body is moving downward with a net acceleration of 5 meter per second square. Now we know that when a body is under acceleration, so inertia force acts in the opposite direction with the magnitude of mass times the net acceleration of the body. So the lift is moving down, so inertia force would be acting upward. Let us denote it by Fi, force of inertia. Weight is acting downward, that is mg. So let the reaction force that is applied by the weighing scale on the man be R. Now balancing, we have Fi plus R equals mg. Here Fi would be equal to mass times acceleration, that is 70 multiplied by 5 meter per second square, that is 350 Newton. So R would be 700 Newton minus 350 Newton, or it is 350 Newton. So the reaction force that is applied by the weighing scale on in the upward direction would be 350 Newton, or the reading would be equal to 35 kg. Now in third case, we have lift is moving upward with a uniform acceleration of 5 meter per second square. So in this case, free body diagram would be something like this. In the downward direction, it is mg force. In the upward direction, since the lift is moving upward, so in this case the inertia force would be acting in the downward direction. So let us represent it by Fi, force of inertia, and the reaction force, that is the measurement. So in this case, R would be equal to mg is 700 Newton, we have discussed it earlier, plus Fi. Here Fi is equals to mass times net acceleration. Mass is 70 multiplied by 5 meter per second square, so it would be 1050 Newton, or it would be 105 kg on the weighing scale. Now in fourth case, where what would be the reading on the lift if its mechanism fails? So if its mechanism fail, then the reading would just be 0, because it would be under free fall and both the object would be falling freely. Let us understand it by mathematically. So let us assume that this is the body, and since it is acted on by the acceleration due to gravity, so its its force on the downward direction would be mg. Now the weighing scale reading depends upon the reaction that it would be giving in the upward direction. So in this case, since there is no reaction, because both the body is falling freely under gravity, so it won't be able to give any reaction force. That's why the net force would be mg on body, on the man, and also on the lift. That is why the reaction force would be 0. So it would be accelerating independently in the downward direction. Thank you. The question says that figure 4.16 shows the position time graph of a particle of mass 4 kg. What is the force on the particle for t less than 0? That is this zone, t greater than 4 seconds. That is this zone, and t between 0 and 4 seconds, that is this zone. We also need to find the impulse at time t equals to 0 and time t equals to 4 seconds. We have to consider one dimensional motion only. So at first we will recall the definition of impulse. Impulse mathematically is given by the expression f delta t, that is mass times final velocity minus initial velocity, final minus initial. So this is the expression for impulse, and the question is asking in the first part that what is the force on the particle for t less than 0. Since for t less than 0 we see that there is no any motion in the particle, so there must be net force that is equal to 0 for this the particle to be static. So we can say that there is no any net force on the particle. Now in the second part, that is t greater than 4 seconds, we have again the particle is at rest. So again we can say that since particle is at rest, so the net force on the particle is 0. For the path between 0 to 4 seconds, the graph is straight line. So when the position time graph is a straight line, it is the case of constant velocity. Again the body is moving in constant velocity, so net force must be 0 because there is no any acceleration. So force is always 0 in all the three cases. So force is always 0. Now in second part we have to calculate impulse at time t equals to 0. Using this formula we can calculate impulse, that is mass times final velocity. So velocity of the particle can be calculated as the distance divided by time interval. So distance is 3 meter, time is 4 seconds, so it would be 0.75 seconds meter per second, and it is constant. So the final velocity is 0.75 minus initially it was at rest, so it would be 0. And now that would be given as the mass of the body is 4 kg. So 4 times 0.75 kg meter per second. So it would be equal to 3 kg meter per second. Now in third part we have the impulse at, no, it is not the third part, it is just the second part of this B. We have to find out at impulse at time t equals to 4 seconds. So at time t equals to 4 seconds, the final velocity is 0 and initial velocity is 0.75 meter per second. So it would be 4 multiplied by 0 minus 0.75, and that would be given as minus 3 kg meter per second. The question says that two bodies of masses 10 kg and 20 kg respectively kept on a smooth horizontal surface are tied to the ends of a light string. A horizontal force of magnitude 600 Newton is applied to A and B along the direction of the string. What is the tension in the string in each case? So the question basically says that there are two masses. The first one is of 10 kg and the second one is of 20 kg. They both are kept on a smooth horizontal surface. Here smooth refers to the surface which has no friction, or we can take mu, the coefficient of friction, to be 0, and we can eliminate the friction altogether. Also horizontal surface here refers to the masses, the force of gravitation that would be acting vertically downwards. So we have to find out what if the 600 Newton force is applied on 10 kg away from the string, and what if the acceleration, what if the force that is 600 Newton is applied on 20 kg object away from the string. So what is the acceleration in each case and the tension in each case? We have to find out both the things. Now let us proceed with the free body diagram of this case A, where 10 kg object is being pulled. So the free body diagram of 10 kg body would be, there would be gravitational force that is acting downwards of magnitude mg, or 10 kg multiplied by 10 meter per second square. Here acceleration due to gravity is taken as 10 meter per second square. Also the reaction force would be acting as r, that would cancel out each other, and this is our force of 600 Newton. Also the application of, due to the application of this force of 600 Newton, this entire system would be in acceleration. So let us assume that the acceleration is in the direction of force, that is along the 600 Newton. So the inertia force would be acting in the opposite direction of same magnitude A multiplied by the weight, mass of the object. So force of inertia would be 10 multiplied by A, that is acceleration. So equating the forces, we will get, also there is a tension force in the string that would be acting away from the object. So there will be T as well. Let us assume it by T. Now equating the force, we will get 600 Newton equals to T plus 10 multiplied by A. And taking this free body diagram for 20 kg object, we will get, let us draw it here. So again there would be 20 multiplied by 10 meter per second square, that is the weight, reaction force, that will cancel out each other. Here T tension is applied, and since the acceleration would be in the direction of tension, so inertia force would be acting in the opposite direction of magnitude 20 times a, because we have assumed the acceleration that which the body will be pulled is a. Now these are the two equations. This is equation 1 and this is equation 2. So from this equation 2 we will get T equals to 20a. So substituting this T equals to 20a in equation number 1, we will get acceleration of 600 divided by 30, or we will get it as 20 meter per second square in the assumed direction, that is in the direction of force. So this is the force, so this is the acceleration that we have got. Now we have to calculate the tension in the string. So tension in the string can be given by the expression T equals to 20a, or in this case when 10 kg object is being pulled, we can say that tension is equals to 20 multiplied by 20, or 400 Newton. So the case where 10 kg object was being pulled, the tension developed is 400 Newton. Now let us consider the case where 20 kg object is being pulled. So let us draw the free body diagram. In this case we will assume that the ball is, we will draw it by just a dot to save the space. Now so for 10 kg object, tension would be in this direction. Now let us assume that the acceleration is in this direction. Let us assume its magnitude be of a. So inertia force would be acting in the opposite direction of the net acceleration. So we can represent it by Fi, and that would be equal to 10 multiplied by a. Now since the weight and reaction will cancel out, so we are not drawing it over here. Now writing the equilibrium equation, T equals to 10a. Let us represent it by equation number 1. Now similarly we will draw the free body diagram for 20 kg object. Now the force is acting in this direction, 600 Newton, and tension is being applied in this direction. Also acceleration is in the direction of force, so inertia force should be acting in the direction of tension, or in the opposite direction of 600 Newton. So we can give it by magnitude Fi, that would be equal to 20 times a. Now equating both the sides, we will get T plus 20a equals to 600 Newton. Now let us represent it by equation number 2. Now substituting this T equals to 10a in equation number 2, we will get a equal to 600 divided by 30. Now again we will get acceleration magnitude of 20 meter per second square. Now tension developed is, we will substitute a in here, so T would be equal to 10 multiplied by 20 equals to 200 Newton. So in this case the tension developed in the string is 200 Newton. Now this is just half as compared to 400 Newton in the previous case when 10 kg object was being pulled. Thank you. The question says that two masses 10 kg and 12 kg are connected at the two ends of a light inextensible string that goes over frictionless pulley. Find the acceleration of the masses and the tension in the string when masses are released. So here string is light, it means its weight is not going to be considered, and it is inextensible, it means the string is not extending upon application of load, and also the pulley is frictionless, therefore we don't need to consider the friction force over the pulley. Now we need to find the acceleration of the masses and the tension in the string. So let us represent the tension in the string by T. Since it is a single string, so the string tension in both the case is going to be same. Now for acceleration, Let us assume that the 8 kg object would be going upwards, so its acceleration is a, and since it is a single string, so it is going to be in the downward direction a. Now let us proceed by the free body diagram at first of 8 kg object. Now 8 kg object is subjected to gravity, so there will be gravitational force of 80 Newton. There will be tension in the upward direction, and also since it is going to be accelerated in the upward direction with the magnitude of a, so force of inertia will act in the opposite direction of net acceleration, that is in the downward direction of magnitude mass times its acceleration, so 8a. Similarly, let us draw the free body diagram of 12 kg object. Weight is 120 Newton. Tension is T. Since its net acceleration is in the downward direction, so its force of inertia is going to be in the upward direction of magnitude 12a. Now let us equate the forces. So in this 8 kg case, T would be equal to 8a plus 80 Newton. Let us term it by equation number 1, and in this case T plus 12a equals 120 Newton. So substituting this expression of T in equation number 2, we will get 8a plus 80 Newton plus 12a equals to 120 Newton. So 20a equals to 40 Newton, that is a equals to 20 meter per second square. Sorry, it's 20a equals to 40 Newton, so a would be equal to 2 meter per second square. Now we can find out the tension in the string with expression number 1, since we know the value of a. So substituting this value of a in expression number 1, we will get T equals to 8 times 2, that is 16, plus 80, that is 96 Newton. So tension in string is 96 Newton and the net acceleration is 2 meter per second square. Thank you. The question says that a nucleus is at rest in laboratory frame of reference. Show that if it disintegrates into two smaller nuclei, the product must move in opposite directions. So the question is underlining the theory of conservation of momentum, which states that total momentum of a system of interacting particles is conserved. So it says that if a system has let's say particle m1, m2, m3, and if it is isolated and the net force acting on the system is 0, so the momentum is always conserved, or the change in momentum is equals to 0. So in our case over here, there is a nuclei and it disintegrates into two smaller nuclei. So let us assume that the smaller nuclei has mass m1 and m2. So according to conservation of momentum, its initial momentum is equals to final momentum, or P initial is equals to 0, and that will be equal to P final. Now P, the momentum, can be stated as mv1 plus mv2, where v1 and v2 is the velocity of mass m1 and m2, m1 v1 plus m2 v2. So according to conservation of momentum, P initial equals to P final, or P initial is equals to 0 equals to m1 v1 plus m2 v2. Now we have to show that the velocity of one particle is in opposite direction of the velocity of another particle if the particle disintegrates. So let us assume that in the final stage the particle disassociates. So v1 v1 can be given by the expression minus m2 v2 divided by m1. So here m1 and m2 are constants, and v1 and v2, their direction is, the sign is opposite, so we can say that the direction of v1 is opposite to the direction of v2. So according to the conservation of momentum, we have proved that the velocity of the particle will be in opposite direction given the momentum is conserved. Thank you. The question says that two billiard balls, each of mass 0.05 kilogram, moving in opposite direction with a speed of 6 meter per second, collide and rebound with the same speed. What is the impulse imparted to each ball due to the other? So we know that expression of impulse, F delta t, stands for final momentum minus initial momentum. Now the case is, let us assume that this is a ball 1 and this is ball 2, and they both are moving in opposite direction with a speed of 6 meter per second, and when they collide, they then rebound with the same speed, that is 6 meter per second. Now the impulse for the ball 1 can be found out using m1 v final minus m2 m1 v initial, and the mass is 0.05 kilogram multiplied by the velocity. Let us assume that this is the positive direction of velocity. Now the v final for ball 1 is minus 6 meter per second minus of 0.05 kg multiplied by, now v initial is in the positive direction 6 meter per second, so that would be equal to minus of 0.3 kg meter per second minus 0.3 kg meter per second, that would be equal to minus of 6 kg meter per second. Now similarly for ball 2, we can find out using this expression. The initial velocity for ball 2 is in negative direction, and the final velocity is in the positive direction, so F delta t for mass 2, that is equals to 0.05 multiplied by v final, that is positive of 6 minus of 6, that is v initial, kg meter per second, and that would be equal to 0.05 multiplied by 12 kg meter per second, and that is going to be equal to 0.6 kg meter per second. So the impulse is of same magnitude, but it is in opposite direction. For ball 1, the direction of impulse is in the opposite direction of initial motion, and vice versa for ball 2 also. Thank you. The question says that a shell of mass 0.2 kilogram is fired by a gun of mass 100 kilogram. If the muzzle speed of the shell is 80 meter per second, what is the recoil speed of the gun? So here the question is trying to underline the principle of conservation of momentum, which states that for an isolated system, the momentum is conserved, or initial momentum is equals to final momentum. So initially both the bullet and gun were at rest, and after the bullet escapes the gun, there must be something to counter that momentum that is gained by the bullet, and the other body in this system is the gun, so the gun must have the velocity that will together combined with the mass will counterbalance the momentum of the bullet. So here muzzle speed of the bullet shell is the takeoff speed, or the speed at which the bullet escapes the gun. So let us express this in the mathematical form. So P, or the momentum initial, is equals to P final. Initial momentum is equals to 0, and mass, so final momentum is comprised by mass of the product of mass of the bullet and the product of the mass of a gun with both of its velocity respectively. So mass of the bullet is mb multiplied by velocity of the bullet plus mass of the gun multiplied by velocity of the gun. So that would be equal to 0.02 multiplied by velocity of the bullet is 80 meter per second plus mass of the gun is 100 kilogram multiplied by the unknown velocity v. So here solving for v, we will get minus of 1.6 divided by 100 meter per second, or we can also express it as minus of 1.6 centimeter per second. So here minus implies that the velocity of bullet is in opposite direction with that of the velocity of the gun. So here we come to the conclusion that the recoil speed of gun is 1.6 centimeter per second in the opposite direction. Thank you. The question says that a batsman deflects the ball by an angle of 45 degree without changing its initial speed, which is equal to 54 km per hour. So a ball approaches the bat like this, and then it deflects following this path, and the angle made by the approach line as with respect to the deflected line is 45 degree, and the speed of the ball is 54 km per hour. So the question says that what is the impulse imparted to the ball. So during the impact, what is the impulse that is provided by the bat to the ball? We have to find out that. So we know the expression of impact, that is F delta t. The impulse can be found out by change in momentum, that is final momentum minus initial momentum of the ball. So here let us first convert this speed in meter per second. So 54 kilometer per hour can be expressed as 15 meter per second. Now the final momentum of the ball is mass of the ball, that is 0.15 kilogram multiplied by its velocity. So for our convenience, since velocity is a vector, let us first decompose the velocity vector in the horizontal as well as vertical component. So we see here that in the horizontal component, let us assume that this is the velocity. So in horizontal component, the velocity remains unchanged. The velocity in the horizontal component is v sine 22.5 degree, and since the ball returns back with the same speed, so again the velocity component in the horizontal direction for departure is v sine 22.5 degree. So the component of momentum in the horizontal direction is unchanged, so it is going to be 0. The impact in the horizontal direction is going to be 0. Now when compared with the vertical direction, vertical component of the speed, so vertical component of the speed is v cos 22.5 degree. So assuming that upward direction as positive, initial direction of velocity was negative, and final velocity after the departure is positive, so there is a change in velocity in the y direction or the upward direction. So impact. So the impulse can be found out in the upward direction as mass times velocity. Initial velocity is minus of v, that is 15 meter per second, cos 22.5 degree, minus initial momentum. Initial momentum can be given as again mass times its velocity, and this time its velocity is in the upward direction, so it is in the positive direction, so we can simply write it as 15 meter per second cos 22.5 degree. Now it can be expressed as 2 multiplied by 0.15 multiplied by 15 cos 22.5 degree kg meter per second. Upon solving this, we will get, taking the value of cos 22.5 degree as 0.924, we will get 4.2 kg meter per second. Thank you. The question says that a stone of mass of 0.25 kg tied to the end of the string is whirled upon in a circle of radius 1.5 meter with the speed of 40 revolutions per minute in a horizontal plane. Now, what is the tension in the string, and what is the maximum speed with which the stone can be whirled around if the string can withstand a maximum tension of 200 Newton? So, in this question, we have been given that stone is tied to a string which is whirling upon, and the radius of the circle of the path of its whirling is 1.5 meter, and the mass of the stone is 0.25 kg. Now, since this string and the whirling of circle is in a horizontal plane, that is, they are in a line, so we can simplify this free body diagram in just two component of force. That is, first is the centrifugal force of mv square upon r magnitude, and the second is the tension developed in the string, which is counterbalancing this centrifugal force. So as the first part of question says that what is the tension in the string, so this can be easily found out using this equation. We have to just find out the velocity, which is given in revolutions per minute, and so we will convert it in meter per second. So let us first convert the velocity in meter per second. So it is given 40 revolutions, means 40 times 2 pi r divided by 1 minute is 60 seconds meter per second, and this will give out a value of 6.28 meter per second velocity. Now we can calculate tension as T equals to 0.25 kg multiplied by V square, that is 6.28 square, divided by R, that is 1.5 meter. So the magnitude of tension is going to be 6.57 Newton. Now the second question says that what is the maximum speed with which the stone can be whirled upon if the string can withstand a maximum tension of 200 Newton. So here in this equation, now we see that we have got tension, that is the maximum tension of 200 Newton, and we have to find out what would be the maximum velocity for 200 Newton such that the string can balance it. So we will solve it for velocity now, given the tension, using this equation. So equation would be 200 equals to, mass would be same, that is 0.25 kg multiplied by V square divided by R, that is radius 1.5 meter. So V would be equal to, that would be equal to 0.25 kg multiplied by V square divided by R, that is radius 1.5 meter. So 1 meter is 60 seconds meter per second. So 60 times 2 pi r divided by 1 minute is 60 seconds meter per second. So V would be equal to, that would be equal to 0.25 around 34.64 meter per second. Thank you. The question says that if in exercise number 4.21 the speed of the stone is increased beyond the maximum permissible value and the string breaks suddenly, which of the following correctly describes the trajectory of the stone after the string breaks? So in the past question we solved out that maximum velocity that can be achieved safely was 34.64 meter per second. Now what will happen if the velocity is increased? So if the velocity is increased, then the tension would increase and it can't be sustained by the string, so the string will break. Now there are three cases that describes the possible scenario after breaking of the string. So in the first case we see that the stone moves radially outwards, and the second that is, let us assume that this stone is here. Now the first case says that the stone moves radially outwards. It means when the string is broken from here, then stone will fly away like this in this direction. Let us assume that its velocity was directed in this way. Now the first case says that the stone will fly away in this direction. This is the first case. And the second case says that, let us assume that V is in the same direction. The stone flies off tangentially from the instant the string breaks. Now it says that the stone is flying in the same direction tangentially. And the third case says that the stone flies off at an angle with a tangent whose magnitude depends on the speed of the particle. So the third option says that with the tangent, let us assume that this is the velocity, and since it is a circular path like this, so this is the tangent also, and the stone is flying with an angle of the tangent, like let us assume that angle is theta. So from first law of Newton's we know that every body continues to be in its state of rest or of uniform motion in a straight line unless coupled by some external force to act otherwise. So what it means is that when on a body there is no net force acting, so there can't be any acceleration, and thus it will continue its state of rest or of uniform motion. So uniform motion here means that the object will go with a constant velocity or speed. So the moment string is broken, what we see here is that it will stop revolving because there is no any tension force that is acting to constrain it in the path, and thus the centrifugal force that was acting in the outward direction will also go. So the body will have no net force, or the net force on the body will become zero. So it is poised that the stone will fly off tangentially in the instant the string breaks, because the velocity is always directed tangentially to the path in a uniform circular motion. So the stone will follow its velocity and it will go in the direction of its velocity. Thank you. The question says that explain why a horse cannot pull a cart and run in an empty space. So for a horse to propel the cart, let's assume that this is the horse and this is the cart that is being pulled by the horse. So at first let us assume that there is a ground. It is not an empty space. So what happens is that horse pushes the ground maybe in this direction, and that leads to a reaction that makes the horse go in opposite direction and thereby pulling the cart. Now if the third agent is not there, then there is no any reaction upon the hopping of horse feet, so there is going to be no motion at all. It explains. Now in second question we have explain why passengers are thrown forward from their seat when a speeding bus suddenly stops. So here the case is that when a bus is moving with a constant speed, let us assume that it's moving at a speed v and it is suddenly stopped. What happened is that the momentum of bus suddenly reached to zero, that is from v its speed reached to zero. Now what was happening initially was that let us assume that this is a person who is sitting on a seat. Now the lower part of the person is on the seat and it is kind of with a solid connection, or due to weight it is fixed, kind of fixed, not fixed but kind of fixed. So when bus suddenly stopped, the lower part of the body stopped, but the head part, maybe it was not as rigidly connected as the lower part of his body. That's why due to inertia it continued its motion and thereby it is pushed in the forward direction. Now in the third question we have, it is easier to pull a lawnmower than to push it. So for this we have to make a free body diagram. So let us consider that this is a lawnmower. Now for the resistance in either push or pull, or for resistance in its movement, there is a role of friction force. Now friction force is defined as coefficient of friction mu and its weight, the body's weight. So friction force, the magnitude of friction force can be given by mu and w, the product of mu and weight. Now friction force is always acting against the motion. So let us assume that the lawnmower is first pulled. So this is the force that is pulling the lawnmower. Now what happened is that weight is acting in the downward direction. Force has a component which will act in the upward direction, the pulling force, and also in the horizontal direction, which will lead to the pulling of the lawnmower. Now the upward component of the pulling force will be responsible in reducing the overall weight. So the frictional force will be reduced because overall weight will reduce and thus frictional force will reduce. That's why it is easier as compared to the case of pushing. So let us now consider the case of pushing. So let us assume that force is acting in this direction. Now when we take the component, then it is assisting the weight, or one of the component is in the direction of weight of the object. So this will lead to adding the weight to the lawnmower, thus the frictional force will increase. Therefore more friction will be encountered when pushing the lawnmower. Now in fourth question we have, a cricketer moves his hand backward while holding a catch. So explain why. Now we know that impulse is given by change in momentum, final momentum minus initial momentum. Now here final momentum is going to be 0 and initial momentum will have some value, and thus force is given by change in momentum divided by delta t. Now when the cricketer pulls its hand backward, then it is increasing time for stopping the ball. Now when the ball is being stopped, the momentum is boiled down to 0, or the delta p has more time to come to 0. Thereby if delta t is increased, force is decreased. If delta t increases, force decreases. Thus the effort to catch the ball reduces when the cricketer pulls its hand backward, because delta t has increased and therefore the ball is being catched easily. Thank you.